probability is the numerical measure of the likelihood that an event will occur. Probabilities will have values that include or are between 0 and 1. It means a probability could be 0, or a probability could be 1, or it could be any value in between. So probabilities are typically seen as fractions or decimals. Sometimes they're recorded as a percent. Let's start with a basic example. It says, a state is selected at random from the 50 states of the USA. What is the probability that the one selected is Montana? So first thing on notation is I would write P for probability, and then I would write Montana in here. That says the probability of Montana, right, equals. Now Montana is one of the states of the USA, so its probability is not 0. It is 1 out of 50 because it is one of the 50 states. In this particular example, we assume that the likelihood of each state being selected is equal. That we're not doing it by population or by the size of the state. Now, the sum of all the probabilities in a sample space is 1. So if I had a sample space that could be described as S, T, U, V, and so on, all the way until Z, if that's my sample space, then the probability of each individual element, when you add each of them together, equals 1. Let's take a look at an example where this can be applied. In a study, people were classified as having either black, brown, blonde, or red hair. The probabilities of a randomly selected resident having black, brown, or blonde hair are 0.17, 0.47, and 0.2 respectively. Assuming each resident has one of these 4 hair colors, question A, what is the probability that a randomly selected resident has red hair? Let's go back up to some language that many people do not understand. In the second sentence, it had said in a list, black, brown, blonde, and then these probabilities with the word respectively. What that means is this 0.17 connects with the probability of having black hair. The 0.47 is the probability of having brown hair, and the 0.20 is the probability of having blonde hair. The order of how the words are provided tells you the order of how to attach the numbers to those words. Okay, so let's go back to question A. What is the probability that a randomly selected resident has red hair? Well, the problem didn't tell me the probability of red hair, but it does tell me that there are only 4 colors that this problem had. There was black hair, there was brown hair, blonde hair, and red hair. So this was all of the items or colors in my sample, which means all these probabilities should add up to be 1. So to find the probability of people having red hair recorded would be 1 representing 100%, or the total that all the probabilities would add to, minus the probability of having black hair, brown hair, and red hair. So this ends up being 0.16. The probability of having red hair is 0.16. Now, let's take a look at part B. What is the probability that a randomly selected resident has brown or black hair? So probability of brown hair, because it says or, we know we want to add these together because we want to know either brown or black. The probability of brown was 0.47. If we add the probability of black, which was 0.17, we arrive at 0.64 as the probability of having brown or black hair. It's going to cover the inclusion-exclusion principle. At the top you see two formulas, and these formulas were covered in some counting techniques. But before they had lowercase n, which stood for the number of elements in these items. Now we're looking at the probability. Both of these formulas are the same as they were before, except that they have probabilities instead of n for number count. The example is, at a college, the probability that a student selected at random is taking a mathematics course is 1/3. The probability that they are taking a computer science course is 1/8. And the probability that they are taking either a mathematics course or a computer science course is 5/12. What is the probability that a randomly selected student is taking both types of courses? Let's begin by identifying what we've been given. I know the probability of a student taking mathematics is 1/3. Now those students included in this 1/3 are students that are taking mathematics and any other courses. So this will also include the computer science students. The probability of taking a computer science course, which I'll abbreviate as CS, is 1/8. So some of these computer science students are also taking a math course. And we know the probability that a student who is taking math or, which is union, computer science is 5/12. We want to know the probability that a student is taking math and, or intersection, computer science. From up above, we can see that we want to use the second formula. The probability of math is 1/3, plus the probability of computer science is 1/8, minus the union of math and computer science. With technology, we could solve that, or we can find a common denominator. And arrive at the answer of 1/24. I'd like to also mention that a Venn diagram would have been applicable in this situation. We would have had math and computer science. Now everything inside of the circle for math would need to add to 1/3. So I can't just write 1/3 in there. One thing I can write is I can write 1/24 at the intersection of math and computer science. To figure out what would actually go in this section of math only and not computer science, I would need to take the math probability of 1/3 and subtract the 1/24. So that's 7/24. And for the computer science section, I would take the 1/8 minus 1/24. And that reduces down to 1/12. So the probability that a randomly selected student is taking both types of courses, the answer is still 1/24. But a Venn diagram could have been used to see that 1/24. We could also verify if we felt like by taking the 7/24, adding 1/24, adding 1/12, which I'll change to 2/24, see that that does in fact give me 10/24, which reduces to the 5/12 that represented the union as it should if I'm adding all of the numbers in both sets.